again, the Kliatchko's work is very general. It is nothing to do with complex number, but mostly we'll concentrate on complex number. It is for any algebraically closed. So X is Toric variety over A, and E is a equivariant bundle. So there is a so when I say toric variety means there is an underlying total which is acting on X and which is sitting inside as a tensor and subset. And T has an action on X. And when I say it's an equivariant bundle, that means that roughly I have a lift of T action on me. T is a vector bundle. T has a lift on X. So what does it mean? That means that if I mean roughly you have some T is a total space of the, so this diagram comes for everything. Okay. So this is like a vector bundle has a equivariant structure if it is it's not that all vector bundle will have a T equivariant structure. So there are conditions that will say that not all vector bundles are T. You can give a T equivariant, and even if you have a vector bundle which has a T structure equivariant, so it need not be unique. Even a vector bundle, there are infinitely many, in fact, equivariants. Okay, so a little bit of some notation I need to fix. So so X, as you, I mean, many of you know that X is determined by some simplicial object. So they are called span, determined by say sigma X. So these are fans. So these are some which consists of some cones in some, if X is of dimension n in a n-dimensional real vector space. So and let's denote n to be the lattice, the one parameter subgroup, and M is the character lattice, which are seen, and M they are dual each other. There is the natural pairing. And if you take two cones, tau and sigma, if they are in sigma X, suppose tau is a sub of a sigma. So basically, these cones they parameterize your orbits. So this each sigma, so T orbits are parameterized by cones. So that means for every sigma, I can associate an orbit which is T orbit, and if I have a subcone, say tau is a sub of sigma, then O sigma is the opposite. O sigma will sit inside tau, and dimension. So what is dimension of sigma? Dimension of sigma is the smallest subspace in Rn. Suppose T is of X is of the dimension n. Then dimension of tau is the smallest subspace of Rn which contains the cone tau. So dimension of sigma is codimension of cosine. So if I take a say one-dimensional cone, which I will call ray, bigger. So if I take one-dimensional cone, so what I get divisors. Okay. So so when I write mod sigma, so these are the vertices of the cone. So this is so okay. Let me write mod sigma x, the generators of the cone. So this is the ray generator of sigma. The generators of sigma. Sigma belongs to sigma A. So and then you write mod sigma as the ray generators of sigma, little sigma. So it will be interesting. So ray generators are somehow important in the classification of equivariant vector bundle. So that's why I want to fix the notation. So this is a theorem of Liachko. So first let me state, well, I will state it for the non-singular case. Huh? Okay. So this is the theorem of Liachko. So which so I assume X is now for simplicity again. But Liachko's theorem is very general. It is for singular toric variety also. But let me say for the non-singular case because I'm going to be on tangent bundle. So so let's X assume for simplicity X is non-singular. So then if you see, so there is a categorical equivalence. Between equivariant bundles on X and certain linear algebra data. So what is it? So they are E indexed by this is a indexed by this rays. Sometime depending. I mean, sometimes I may write rho or alpha. Alpha and rho they are all the same. I mean, I sometimes may write rho. I mean, there may be a mix. Okay, because Liachko's notation he writes alphas. Anyway, so alpha is in sigma 1. So all one-dimensional or sigma x here. Instead of x and sigma 1 because the and this I is in I are integer. So what are these E alpha I? So these are decreasing filtrations. E alpha I is a decreasing filtration of E. So that means E alpha I subspaces. And so at some point it is, so it's a finite, E is a finite dimensional vector. Basically this is finite dimension. This will be the rank of the bundle E. And this is at some point it will be 0. Right. So So how do you get this from the so basically very quickly I will say that how do you get this filtration?
Equivalence of categories to what is the model.
Here map is map of vector space which takes this filtration to the other the natural maps. Okay, so very quickly I will say what is E alpha I. How do you get E alpha I? So E alpha I is all those E. So let's fix the point. Say in the identity, if I call it X naught. So E belongs to X naught. So that limit. So for every alpha that will correspond to a divisor, and every divisor has a unique fixed point. Let's call it X alpha. So, because it is in the boundary, you can go via T. So you consider only those T which takes X naught to X alpha. Right. So this is how Kliatchko defines. You can define another way of you can define it when the variety is not smooth using the isotypical decay model. But this is another way of defining. So this exists. This is so now you can see that there is a chi. And here is a I. What is the relation between chi and I? So basically, it is chi of alpha. There is a pairing between on-parameter subgroup and the characters. So this is I. And this does not depend on chi. A priori, it should depend on chi, but it actually depends on chi and alpha. The pairing of chi and alpha. So that's why there's I. So this is, and you can see that easily that it will be a decreasing filtration if you define it. So this was, and not just this, there is a one which is very crucial condition, is plus some condition which Kliatchko calls compatibility condition, that it says that this E alpha I is this there is a distributive lattice property plus distributive lattice. So what is distributive lattice property means? So there is some kind of compatibility required for the so that means that there is a basis B of E, but when you B intersect with E alpha I, that's also a basis of E alpha. So that means there exists a B, a basis of E, such that B intersection E alpha I is also a basis of E alpha for all alpha for all I. This is a very strong condition. So checking if you have a collection of vector subspaces, whether such B exists or not, it's not an easy condition. So I mean, this is a very strong condition. I mean, but one can one can make it more in another way. You can using the isotypical decomposition, one can make it nice. I mean, you can change a little bit, which for the non-singular for the singular case. But anyway, I will not go into that because I don't need it for this stage. So the point is that I should say that E alpha I does not depend on chi. This does not depend on. When you define it, if you use it does not depend on chi because certain extendability condition. So this is Kliatchko a big theorem, which is a very useful theorem because study of equivariant bundles on two varieties. So this got generalized for equivariant sheaves, which I will come into in a moment. And okay, so but let me say a few things about this theorem of Kliatchko. Using this theorem, this Kliatchko proved Horn conjunction. It was the biggest application. So, which when we are studying vector bundles on P2, studying vector bundles on P2, Kliatchko proved that's a, I mean, there's a, but there are some other bundle theoretic question. One can everything about equivariant bundle you can translate into this linear algebra data. Like if you want to compute the cohomology of Hi of Xc, so for x equal to Pn, you can do it using filtration data. For when x is not equal to Pn, you can compute at the H0 and Hn, the zeroth and the sections and the top order term. And other things like if you have an equivariant bundle, when it splits, that also from the data you can determine. So I will just quickly say a few things. So, but okay, let me say a few things about equivariant bundle before going into stability. So without Kliatchko, one can prove such. We don't need Kliatchko description. One can prove these facts that I was saying that when a vector bundle has a equivariant structure, one of them is that E has equivariant structure. If and only if T upper star of E is E. Or sometimes I should write child E because it corresponds to the vector space. And E is equivariant. Is X is say I assume X is complete. Then E is decomposable. If and only if it is equivariantly decomposable. So this says about your splitting property that if it splits, then it is equivariantly splits. And if you have, say, for these things you don't need Kliatchko. Using T action, one can prove such things. I mean, but just a little bit some properties of equivariant bundle I'm just got right. So if E is isomorphic to air, non-equivariantly, need not be an equivariant isomorphism. Then there exists a character. A character gives you a line bundle. Then E is isomorphic to some. And using Kliatchko, if using Kliatchko, one can prove such some results, interesting results. Like one thing is that the line bundles are given by a bunch of integers, so that is not a very interesting. But let me say something that a rank 2 when a rank 2 bundle, rank 2 equivariant bundle splits. So this question, if you ask, from the filtration, I can, if you give me the filtration data, I can tell that whether it's fixed or when you're looking at it. And for smooth, this is another interesting result. When X is a smooth surface, dimension of X is 2. Then there is no compatibility condition. See, like I said, that this compatibility condition is really hard to check because giving a filtration is okay. I mean, you give a filtration of subspace for every alpha, but this distributive lattice property, whether everything, each component, whether they are from there, it's generated. I mean, those basis element is the basis element of here. That's a hard thing to check, especially when you have more and more rays. As your toric varieties become more and more complicated, now you have more number of rays, so you have more check. So so compatibility condition, there is no compatibility condition. So compatibility condition is redundant for when X is for toric surface, smooth surface. And the crucial thing, which is again requires some thought, but this is very crucial in our case. If you take the tangent bundle P of X, so if I write it like dx, and if the corresponding Clearchko filtration is, let's say I write T for the vector space, then the filtration data is T and T alpha I. Right? So this T alpha I is given as some, which is a one-step filtration. T alpha I is n tensor, you say K. But n is a one parameter. So this is when I is less than equal to 0. And this is generated by alpha. And when I equal to 1 and equal to 0, when I equal to. And if you know Clearchko filter, you can do, if you know for Clearchko filtration for a vector bundle, you can know its dual, wedge product, direct sum. Direct sum is just direct sum of vector space and direct sum of the sum of the filtration. So, the tensor product is just the usual Cauchy product, like the way we multiply sequences. Okay, so those things can be done. I mean, so those things are there. Functoriality, nice. If you know, nice. So anyway, I will not go into detail all about it. So I'll stop here with the, but now I'll come to the stability. So I will not go into definition of stability because I assume that no. So it's like you fix a polarized surface X8. X is smooth. H is a very ample line bundle or divisor. Then you define your I am interested in slope stability. So if I have a vector bundle E on X, then I define mu of E, vector bundle, is degree of E times rank of E. So this is nothing but C1 of E, and this is take H power n minus 1, if any is dimension of X. By Now you say E is semi-stable or stable if you have for every F sub E, and you can assume that E mod F is torsion free, that means F is saturated. For every saturated subsheaf. So these are called when you, so this is due to Langton. This definition was given in Langton's, I think, first time. Sorry, Langton's paper where he proved the boundedness. Where she proved the boundedness. So mu of F is less than equal to mu of E. And look at in the Langton for details, or some book of him. If you are not familiar with this definition, sorry. So stable if the streak inequality, and if it is not streak, then okay. So now see, you are interested in if you are interested in semi-stability of some equivariant bundle, suppose E is equivariant bundle, you have to the subsheaf of the bundle is not a bundle. So yeah, so you have to come down to sheaves, so equivariant sheaf. Exactly same way one can define what is the equivariant sheaf. Again, it is due to Mumford, I think, for where he defined for using the equivariant sheaf for GID purpose, he needs it. So it is done, I think. Mumford book, you can see the definition of equivariant sheaf. So I assume that T action equivariant sheaf. So now this result actually Kliachko, after this paper, Kliachko wrote a preprint about equivariant torsion free sheaves. But that paper never got published. And that paper had some, it was not a complete, proofs were not given. It was more like a sketch. But then it got rigidified by Parling. So I think Kliachko after this, I forgot the year, somewhere in '94, I think. It is a Max Planck preprint where he generalized this definition of this Kliachko description for torsion free sheaf, but never published it. But then it got published in 2006, around 2006, I think, if I am right, 2006 or 4. Little bit I have confusion. So by Parling, so he generalized Kliachko's theorem for equivariant torsion free sheaves. In fact, he does it more generally equivariant covariant sheaf, but later, and for torsion free sheaf, you have a nice description. But again, see, I will be more. So description of torsion free sheaf is more complicated. It involves the multi-filtration, not just one filtration. It's called multi-filtration. So it will be more complicated, but for our work purpose, we are interested in subsheaf of some bundle. Tangent bundle is a bundle. So if I take a subsheaf, saturated subsheaf, the saturated subsheaf of a reflexive sheaf is reflexive. So it is enough to know what are the reflexive subsheaves of the reflexive sheaf. So that's why. So reflexive sheaf. So the description of reflexive sheaf is easier to handle. That's what Parling proves. That the description of equivariant reflexive sheaf, category of reflexive sheaf, you don't need this compatibility condition. What he defines compatibility condition, which is like in the case of locally free sheaf, he defines some compatibility condition, which is again like complicated condition. But you need, but reflexive sheaf, you don't need that. Just filtration is enough. Just like surface case. So I will just write. It was done by Parling. So category of equivariant reflexive sheaves. So again, this is one the categorical equivalence between this and this. Again, E is a vector space, finite dimensional vector space of rank of the bundle. And here you have only the way he get this E. It's not, see here, Kliachko evaluates at the point x0. That's how he gets it. Here he does not give, he does it in a roundabout. He takes space of section, which is infinite space over the open set, and then he gets a isotypical living. But as a result, what he gets here, the Kliachko filtration was decreasing. In the Parling case, only difference is that it is an increasing filtration. So that's only one point to note. So this is an increasing, E alpha I is an increasing filtration. That means E alpha I is sum of E alpha I plus 1. Like this. Of course, it is finite, so it will stop some point. E is the dimension of E is the rank of E. Rank means the rank of the torsion field divided on the open set. Okay, so this makes just now I said that to check. I will just a remark. I'll write down here what I said. Remark. Check semi-stability or stability. Check stability or semi-stability enough to work with semi-stability of E, any sheaf E of a reflexive sheaf, sorry, of a sheaf. Enough to know what are the saturated or reflexive sheaves. So this is one of the thing. Another observation is that which was made in our paper that equivariant when you say equivariant stability and semi-stability, they are equivalent, and usual stability, yes, equivalent. So this is this was proved in our one of our earlier paper, the joint work with Indranil and Moina Kudar and Ozan Singh. So this we proved. Actually, this was this was known further by before we gave another proof. This was known by Martin Poole. Poole also had a proof in his paper, where he studies moduli of sheaves, T-equivariant sheaves. So pure sheaves. I mean, I should have said that after Parling's work, this work has generalized for equivariant pure sheaves. Just like the way Simpson did it for pure sheaves. Exactly. So T-equivariant pure sheaves, the Martin Poole has generalized this result of Kliachko and Parling in case of pure sheaves. I should have meant that. Yeah. And he studied the semi-stability, Giesecke semi-stability, Giesecke stability in the. So there he proved he had this semi-stability rather. Okay, so now you see that equivariant. So to study, so if you have an equivariant bundle, which is an equivariant reflexive sheaf, you just need to know what are the equivariant reflexive subsheaves. That's all. If you can classify them, then you are in good shape. I mean, good shape means, of course, you need to calculate the mu's. As your toric variety becomes more and more complicated, calculating will be more and more complicated, of course.
The equivariant stability and the stability as why do you need equivariant reflexive sheaf? Just equivariant.
No, because
I mean, just reflexive sheaf, absolutely.
Yes, but they are hard to, because after all I come to the clear filtration data, I know what are the equivariant reflexive subsheaves. So that's a smaller collection, right? Subsheaves are more. They may not be equivalent. So if you, of course, you have, when you want to check something, it is better to check on smaller data.
But stabilizing subsheaf always have a G. Always have a G.
That is fine. But when equivariant is, but enough to work with equivariant subsheaf. That's what I. So I know how to classify equivariant subsheaf of a equivariant reflexive sheaf. Very easy. I can say that.
And one more question about the equality between equivariant stability and stability.
Yeah.
So, for
Mu stability.
it is a stability.
I think so. Semi-stability is, yes. You have this mu stability is inside chi stability, right? So equivariant chi stable will say that equivariant mu semi-stable. So it will say mu semi-stable. I don't
But
know.
all this follow from that concept that it is decomposable.
I don't know.
This proof is something. This proof of this statement requires.
Probably you don't need mu semi-stability probably. I thought about it, but right now I don't remember actually. Probably there are some. I don't remember exactly what. There may be some issue, but semi-stability it is true. Is like that. You can look at Poole's paper. I think. We thought about it. I don't remember exactly. Anyway. Okay. So this is what the next proposition. How much time do I have? 20. So proposition. Suppose E is a reflexive sheaf. Okay. Then equivariant reflexive sheaf. And has one-to-one correspondence. So suppose E is given by Perling, E increasing filtration. Given reflexive subsheets, there is a one corresponding with subfiltration. So I write it here. Where F is a subspace of E, and F alpha I is nothing but E alpha I intersect with F. So because of this simpler description, in the case of tangent bundle, we are able to, and tangent bundle has a two-step filtration. So these two facts actually, in some cases, you are able to prove that it is equivariantly semi-stable or equivariantly stable, which by that theorem it is stable or semi-stable. So and further E is semi-stable or stable if you have some in terms of filtration data, summation minus I dimension of F alpha I. The similar term here, 1 by dimension of E. Dimension of, So this is you can translate the semi-stability and stability condition in this for reflexive subsheets. Okay, so now I will not. The calculations are very involved. So, but what we are able to prove, I will just say. So maybe it's not a good place to do calculation, but I will say so the results what we got. So obvious first step is to check that x equal to Pn. The Pn, tangent bundle is stable. So with respect to the anti-canonical line bundles. So first of all, I should say my co-author. So this is with Jyoti Dasgupta and Vivash Khan. So, and some of these results are also we obtained before in the paper with Poddar, Indranil and Ozal. But they are for small dimension. We could calculate. The method we used there was very much toric in the polytope using the volume of calculation was more complicated. But we could prove for this from some cases. Of course, for PN we could do. So they overlap. I mean, there is a. So okay. So T PN is stable. So for the Picard rank 2, So this is very nice for toric variety with Picard number 2. So they are actually projectivization of a split bundle over a toric variety of Picard rank 1. Just so that's what Klein-Schmidt. So when P, then there this is so X is of this form P O say PS projectivization of this A1. In this case, so whenever you have Picard rank 2, you have to the line bundle is like AD plus B. So you have to be careful with the polarization also. So first is that P of X is unstable with respect to any polarization I assume the A1s are in increasing order. A1 less than equal to A2. And of course, AI is greater than 1. AI is greater than. So, Tx is unstable with respect to any polarization whenever A1, A, R is not equal to. So in most cases, they are unstable. Okay, and when x equal to projectivization of OPR times some R, sorry, there should be OPS times some R plus say OPS of 1, OPS of A1. Then and H is A of say D, B naught. These divisors are given by rays. Is there any problem?
No.
B of D, B naught. It will be greater than 0. Then you have a condition that Tx is semi-stable if and only if some complicated condition.
So is it the Picard rank you wrote 2 and then you wrote 8? No, not Picard rank. Picard rank.
Library is a projective space. It's a projective but
Projective bundle.
no, it's a very standard group.
Not Picard rank. Rank of the nearest rank of the nearest.
That's a projective space. The primary is projective space, base is projective space. It's only projective space.
Fiber is Pn, right?
Oh, you wrote it.
So it's a little complicated, but I am just so involving R, S, A, B. I have some condition. R minus 1 plus S I times A to the power R minus 1 plus S minus I B to the power I less than equal to S R plus S. I think I have noted it down correctly. Maybe summation R plus 1 plus S or R minus 1 plus S I R minus S. I think here you have some I. I think here I is from R minus 1 to some R minus 1 process. So in the other case, when it is 0, 0, when it is of, then Tx is, so you are giving a full answer then for Picard rank.
So unstable means not semi-stable.
Not semi-stable.
Not semi-stable.
Okay, so as a corollary, you can tell that, see, for example, you will have some condition on A1 into AR when X is fan out. So as a corollary, so A1 is some bound on sum of AIs. So summation AI, if it is less than S plus 1, I think, then it is a fan out. So in case of fan out variety, you are able to say when they are stable and when they are semi-stable for Picard rank. You are giving a complete answer. So for Picard rank 2, you know, you give a Toric variety, I know whether tangent model is semi-stable or stable. So here,
Once you know the classification, then also you
classification for Toric variety is there no one.
product also you say you have this particular form.
Yeah.
Then also you need all this in
Yeah, everything you need, yes. Everything you need. Reflexive substitutes.
very important in the equivariance.
Equivariance, yes. I am using equivariant stability or equivariant semi-stability, and they are equivalent to stability and semi-stability. Because tangent bundle is equivariant. Okay, so, and I should say here that at the same time, some results came also by. So they also had a different result for Picard rank 2. I think I am writing it correctly. Eringa, Neil, and Seuss. They also had a similar result using little different technique. Okay. So, and now recently it is generalized for logarithmic tangent bundle. So whenever you have tangent bundle, next question is for logarithmic tangent. I mean, you add some divisor and then logarithmic tangent shift or flip or logarithmic tangent bundle. Some results are for Picard rank 2. It is done by Napame. For logarithmic tangent. For the Toric variety, for probability for not, I don't think. No. Yeah. Tx minus log b is true for trans. So it's shift. Yeah, you have some fixed Toric divisors. D1, D2, those divisors will come into the some combination they will take. And I don't know, I have not studied the paper, but recently it came 1 month back. And like I said, some of these results were already there in our previous paper. with Viswas and point out that what's up. Okay, so now the next question is a picogram number 3. What happens? So next. For Picard number 3, and so for okay, so of course you have to be more restricted, like you have to be Fano. So Fano toric four folds. Picard number 3, smooth. So then when you have Picard number 3, then and with respect to the anti-canonical divisor, polarization is equal to negative of the anti-canonical divisor. So with respect to minus kx. So these are classified by Batirev. Fano toric, so Batirev classified. So isomorphism classes of Fano toric fourfold with Picard number 3, and there are so all toric, nothing to do with Picard number 3, but I can do it for Picard number 3 only. Fourfold for Fano toric fourfold. There are 128 types, and among them 28 are of Picard number 3, and among these 28 there are 6 stable, 3 strictly semi-stable with respect to minus kx, and 1 and rest unstable. That is for Fano fourfold with Picard number 3. One can using the method. See, dimension I can do it for 4 only. For arbitrary damage, maybe the things will be complicated, so we cannot do. But theoretically, you should be able, because if you know reflexive subshifts, how to calculate them. But the things becoming the sub classification of subshift becomes more. And also, there are another result which is there's something called pseudo symmetric Fano toric variety. So using this criteria, pseudo-symmetric toric variety. So on such toric varieties, it's like Del Peso's product of projective space and product of Del Peso variety. Blow-ups of so on such, one can construct indecomposable rank 2 bundle. So I'm not writing that, but there are results. Okay. So this is about vector bundles. So just how much time I have? Not much. Over. Okay. Just one word that because in the abstract I said I will talk about principal bundle. So principal bundle also we prove that equivariant stability and equivariant semi-stability are same. What toric principal. One can define what is toric principal bundle, just like group action of principal bundle. One can prove that equivariant stability and equivariant semi-stability are equivariant stability. Using Ramanathan's this I will stop.
Thank you very much. Are there any questions? See, can you have some polarization where all these bundles stable? This tangent bundle becomes stable.
Here also I have, if you just take P1 cross P1, tangent bundle is just direct sum. That seems to be well same stable.
Yeah.
You're saying it is unstable.
Where?
So in the simple case, if I take PS to be P1 and X is just P1 cross P1.
PS to be P1,
Second.
S equal to 1.
Yeah, O direct
Equal
sum
to
of
1, R equal to 1, and U1 equal to 0.
P1 equal to 0, yes. Then produce product of Fano variety.
tangent bundle is just.
Tangent bundle is semi-stable.
But you seem to say it is unstable.
This one?
Here it is U1.
But with unless see when it is not, I think I'm writing it correctly. Let's check. Maybe I will. Maybe we can talk later. Yeah, I'll stop.
Are there any more questions? So let's thank the speakers again.
Yeah, borrow more. Maybe we can. You are asking something.
No. You didn't answer the question. I'm asking
So welcome back. So our second talk is by Dr. Akash Gupta from Columbia University, and he is going to speak on a radical Sylvester-Gallai theorem for cubics.
Hey, great. Yeah, thank you very much for the invitation. I'm very happy to be here, and thanks to all of you for sticking around the last day. Okay, so I'll talk about the radical Sylvester-Gallai theorem, and everything I talk about is joint work with Rafael Oliveira, who is at University of Waterloo. Okay. So first, I'll start by talking about the classical Sylvester-Gallai questions, which people have studied. So it starts from, so let's talk about linear Sylvester-Gallai. So I'll write SG for Sylvester-Gallai. Okay, so it was a question of Sylvester in 1893. Okay, so Sylvester asked this question that let's take a finite set of points inside of Rn. Okay, so we have a finite set. Okay, such that it has this property that for all, if you choose 2 points inside of your set, which are not equal, it's two distinct points, and you draw the line joining them, there will be a third point from your given set on that line. Okay, so for all P1, P2, the line L joining P1, P2 contains a third point from our set. Contains a third point P3 in, so P intersection L, and P3 is not same as one of the two points we started with. Okay, so this is the setup, right? So if you have such a configuration, we call it Sylvester-Gallai configuration, and then Sylvester asked, well, do all the points have to be on the same line? Okay, so the Sylvester's question was, so are all points in P collinear? Okay. Okay, so this is the earliest question in this kind of thing. And so the answer is yes, it's very easy to prove. You can, like, high school students can do it. Okay, and so it was proved by Melchior in 1940 and also Gallai 1949. Okay, so the answer is yes. Okay, great. So this is the earliest question. And then, so let's note that the same thing does not work if you replace R with a finite field. So if you have a finite field, let's say f cubed to the power n, you take all the points on your vector space. It's a finite set, right? And then it will satisfy this property, but they won't be collinear. Okay, so it doesn't work over finite fields. Okay, so no for finite fields, general, right? So no for finite fields. Okay, now we can ask, well, what about over complex numbers, right? So over C, okay, same question. So the answer again is no. Okay, it does not work. Okay, example is, let's take, so we can consider inside of Cn, right? Or we can consider, inside of the projective space. It's kind of the same thing. So, okay, so I'm going to give you a set of points which satisfy this property, right? So how do we find them? So let's look at this curve, x cubed, y cubed plus z cubed inside of CP2. Okay, and so this curve, so this is a cubic curve, smooth cubic curve. It has 9 inflection points. Okay, so P is the set of inflection points of, let's say, this curve C. Okay, and then these points have the property that the line joining any two of them contains a third one from your set. Okay, but they are not all collinear. Okay, so P not So P is not collinear, but it's a Sylvester-Garai configuration. Okay, so by that I mean it satisfies this property. It's SG configuration. Okay, any question?
Yeah, what about theory?
Yeah,
What about theory?
I don't know the answer. Okay, sorry. Something else. Okay, but so okay, and if you want,
How does one look for such a set?
how does one look for such a set? I will come to that. That will be one of the motivations why we are studying this question.
Have similar for other Fermat surfaces.
Yeah, if you have, oh, you mean like points on Fermat surfaces? Yeah. Yeah, this will work on any like elliptic curve, right? And but yeah, we don't need Fermat. You choose elliptic curve and choose like inflection points. This will do it. And yeah,
Higher degree, or it's not possible in higher degree, or there are.
higher degree. So there are some other. So it's not known if you choose. Yeah, there are a lot of questions which I don't have answers to. Yeah, but I have answer to one question which I'll talk about. Yeah, but these are all interesting questions which I'm not sure if people have already studied. But I think that would be a big no answer. No, okay.
If we change the triangle size is triangle, put this 3 point. You can prove that there does not exist 3 point collinear point.
Okay.
So
Okay, great. Cool. Okay, right. So wait.
Does the question make sense? Does the question make sense over QP?
Yeah. Right. You can take any vector space and define it, right? Any projective space and then take lines.
Okay. So does it make it easier? I was wondering. Yes.
Sorry?
Okay, fine. Anyway, thank you. Sorry, no. Just a question.
Okay. Yeah, I think we can formulate the question over any field, right? And then whether it works or not, I don't know. Yeah, I think. Okay. Right.
Yes, it's a kind of roots of unity. They are all algebraic, right?
Right. Yeah.
So on an algebraic extension itself, it will fail. If I replace Rn by some other algebraic,
Yeah. Right. Yeah.
like the vector space where all these solutions lie.
Yeah. That will work. Right. Yeah. Sure. Okay. So they're not collinear, right? But they're all inside a plane. You can take, right? You can choose some line, pretend that that's the hyperplane line at infinity, and then everything is inside of C2, right? So then Serre asked this question in 1966 that are SG configurations inside of Cn always planar, right? Or let's say CPN. So Pn, C always planar. Okay, so inside of P2 you can find non-collinear things, but do they always have to be inside a projected plane? Okay, that's the question, right? That was Serre's question, and the answer to this is yes. Okay, so this was answered positively by Kelly in 1986. Okay, so yes. Okay, and how did Kelly prove it? Kelly used Hirzebruch's work on line arrangements on P2. Okay, so using Hirzebruch work on line arrangements. Okay, and which in turn uses the Bogomolov-Miyaka-Yar inequality for surfaces of general type. Okay. Inequality on surfaces of general type. Okay, so there is some like interesting algebraic geometry behind the proof of this. Okay, and so since then there has been a lot of work in this area by computer scientists. Okay. So they were interested for this question for different reasons, but they also gave a proof of this Kelly's theorem. Okay, and they also have generalizations. So I'll state those generalizations, and then I'll talk about something else, the algebra geometry problem that I'm interested in. Okay. How much time did I spend? 10 minutes. Okay. Okay, right. Okay, so the same theorem, right? The Kelly's thing, it was later again proved by other people. So later, more elementary proofs which don't use so much algebraic geometry. Okay, so by Elkes, Pretorius, and so on. Okay, so in 2006. And then later it was proved by Zev de Beer, Saraf, and Wiggers. Okay, so this proof just uses linear algebra, and this is also elementary. Okay, right. So they reproved this thing, and they did something better. Okay. So they did something better. So better, which is the robust version. Okay. So initially, remember, what were we assuming? We have a set of points. The line joining any two of them contains a third one. Or you have a set of vectors inside a vector space. The span of any two of them contains a third one. Okay, that's our condition. This time, they can relax this condition. So let's call it a delta Sylvester-Galai configuration. Okay. So what is our setting? We have a set of points inside a vector space, right? And let me say algebraically closed field of characteristic 0. Okay, so this is the setting we'll be in from now on. Okay, or maybe, yeah, let's just say C. Okay, so I'll just take to C. Okay, I have a set of points inside this C vector space over C, okay, of arbitrary dimension. Okay, and let's say we have m number of points. Right, the cardinality P of P is m. Okay, so we call this set a delta Sylvester-Galai configuration if, so delta SG, if for all Vi, you pick a vector inside of B, there exists delta m number of other vectors which satisfy the Sylvester-Galai condition. If there exists delta m number of Vj's inside of B such that there exists a Vk in the span of Vi Vj, and of course Vk is not equal to Vi or Vj. So if we take delta equal to 1, that is our Sylvester-Galai condition. Okay, so given a vector, for any other vector, there is a third one in their span. This time we are saying that it only works for a fraction of the rest of them. Even in this case, they can bound the dimension of the span. Okay. So previously we said dimension of the span is at most 3. So this case, even in this case, the theorem.
In other words, you don't demand for all pairs.
We don't demand for all pairs, just some fixed fraction. Yeah. So this delta is fixed. So the dimension of span will depend on delta.
But that subclass is well distributed, or is there any such?
Yeah, there is no restriction. As long as for any vector you can find delta fraction of other ones which have this condition, it's okay. Okay. So in this case, their theorem is that, okay, so this is the theorem of Barak, Zabir, Wigderson, and Yehudioff. Okay, is that dimension of the span of our set P is less than 13 over delta square. Okay, so essentially we can bound the dimension of Sylvester-Galai configuration. Earlier they had to be coplanar there, now they can have at most this much dimension. Okay, all right. So this is the theme of these Sylvester-Gallai configurations, is that they are always low dimensional, or we expect them to be low dimensional. Okay. Okay. Okay, let me just say there is also a colored version. I'm not going to state, where instead of taking one set, you take three sets. Let's say red points, blue points, and green points inside of our vector space. And the condition is pick a vector from R, pick a vector from P, then there will be a vector from G in their span. Even then, you can prove that this is small dimension. Okay, so colored version also Sylvester-Gallai works. Okay, so I'm not stating this because this we won't be using it. We'll be doing something different. Okay, Sylvester-Gallai works, meaning that it is small dimension. Okay, so the question in general is, are Sylvester-Gallai configurations always low dimension? Okay, for example, can we bound the dimension of such things? Okay, so now when I say Sylvester-Gallai configuration, I have to say, what does it mean to say Sylvester-Gallai configuration, right? So the kind of Sylvester-Gallai configuration I'm interested in is a non-linear Sylvester-Gallai configuration. We don't have vectors in vector space anymore. We will have polynomials inside polynomial ring. So that is the question I'm interested in. So this is non-linear Sylvester-Gallai. So polynomials and Sylvester-Gallai. Okay, great. So let's do this. So this time, right? So remember the previous, like the first theorem, right? Over C. You have a bunch of vectors in Cn. If they satisfy Sylvester-Gallai condition, then their span is bounded by 3. Okay, or they're coplanar in the projective space. Okay. So we can think about that same statement in a dual way. Okay. So it's the same statement. This time I'm going to look at a set F inside our polynomial ring. Let's say x1 up to xn, n variables, a finite set of forms, a finite set. Okay. And let's say set of linear forms. Okay, so homogeneous linear polynomials, right? So they correspond to vectors inside Cn, right? And we can say that, well, suppose for all Li, Lj inside of our set of linear forms, right? And I not equal to j, and they're all distinct forms, there exists Lk from our set such that Lk is in the span of Li, Lj. Okay. So Lk is in the span of Li, Lj. Okay, and Lk is not equal to Li or Lj. Okay, it's the same thing, just dual. So it has to have constant. So dimension. So this will imply that dimension of span of F is less or equal to 3 by Kelly's theorem. Okay? They have to be in projective plane, so in C3, right? Okay, any question? Okay, so we have a bunch of linear forms such that you take any two of them, there's a third one from the set in their span. Okay, and then they must have small dimension. Okay, now how do we generalize this to higher degree polynomials? Okay, so first thing I'll talk about how to generalize this and why is that generalization interesting, and then what we prove about this generalization. Okay, so now what is our condition we're looking at? So note that Lk is in the span of Li, Lj. It is same as saying Lk is in the ideal of Li, Lj, right? which is also same as saying Lk is in the radical of the ideal Li Lj. It's the prime ideal. Okay, and this is the condition we want to look at. That's why it's called a radical Sylvester-Gallai configuration. Okay, so let me define what is a radical Sylvester-Gallai configuration, and then what's the main conjecture. Okay, so radical SG configuration. Okay, so now we have a set of homogeneous polynomials, a set of forms of any degree inside of our polynomial ring. Okay, let's say, okay, let's just write C. So we have C, x1 up to xn. Okay, so F is a set of forms. So by forms, I mean homogeneous polynomials. So I will call this set a D-radical Sylvester-Gallai configuration if the following things happen. Okay. So number one, all the polynomials in F are irreducible, okay, and degree at most D. That's why it's a D-radical. Okay. So let's say F is equal to this collection F1 up to Fm. It's a finite set. So Fi is irreducible and degree of Fi is less or equal to our fixed number D. So we have homogeneous polynomials of degree at most D. Okay, so that's the first thing. And number two, I wanted all the linear forms, they don't divide each other, right? Then they're not in the projective space, they're different points. That's what we want. So here we want Fi does not divide Fj for different ij. So Fi does not divide Fj for I not equal to j. Okay, so these are natural conditions to put, right? They're not multiples of each other, irreducible forms of degree at most D. And then what is the radical Sylvester-Gallai condition is exactly this. So number 3 is for all ij, I not equal to j, right? There exists k such that Sk is in the radical of Fi Lj. Okay, and k is also not equal to I or j. So this is the setting. We have a polynomial ring Cx1 up to xn, right? And then what are we doing? We pick a bunch of polynomials, homogeneous forms of degree at most D, and we have this condition, they're all irreducible, degree at most D, they don't divide each other. And number 3, you pick any two forms, there is a third form which is in the radical of these given. Okay. That's the setting. This is the generalization. Any question? You can ask the same question for ideals, right? But if we solve for radicals, for ideals, right? Because if it's in the ideal, it's in the radical. And also, radicals come up naturally from the motivation, which I'll talk about in 2 minutes. Okay. So, other questions? So similar to this question, are Sylvester-Gallai configurations always low dimensional? We want to ask whether these Sylvester-Gallai configurations also low dimensional. Okay, similar to this question, there is a conjecture. Okay. So this is a conjecture by question.
One says Fi's are irreducible. And the second condition, some dividing.
Oh, okay, great. Yeah, thank you. Right, so this means that they are not scalar multiples of each other. Right? We don't want them to be scalar multiples.
They're not same.
Yeah, yeah. It's not like I have F and 3F. We don't allow scalar multiples. That's what it means, right? And we can also formulate for non-irreducible things, but I'm sticking to irreducible.
Homogeneous, does it make any difference?
Sorry?
You are taking homogeneous polynomial.
It does not. We can homogenize and do the same thing.
It makes difference that when you take a scalar multiple, it may go wrong.
Right. Yeah. Because But yeah, we sort of want to look at them as points of projective space.
Define not equal to it.
Yeah. Yeah, if you normalize, we just want distinct. Okay, so then there is this conjecture of Gupta, who is a computer scientist. So they conjectured that there exists a function lambda taking natural numbers to natural numbers such that, okay, so what do we want? We want to bound the sort of dimension of this, but the bound should only depend on the degree of the polynomials, not on the number of variables. That is what happened for vectors in vector space. It does not matter how big the ambient vector space you start with, you always get small dimension. Okay? So here also, it should not matter how large the number of variables are. The only thing that should matter is the degree of the polynomials. Yes, that is the conjecture, that there is a function such that if f is a degree d radical Sylvester-Galai configuration, then so they conjecture that the transcendence degree of all the polynomials in F is less or equal to lambda d. So meaning I have a Sylvester-Galai configuration, and the conjecture is that the transcendence degree should be bounded by a function of just the degree, independent of the number of variables in the polynomial ring we start with. Okay? So that's the conjecture. So instead of vector space dimension, they conjecture for transcendence degree. But so far, it looks like it's probably true for vector space dimension also. This is what theorems will tell us. Okay? Any question? Okay. So similarly, you can also ask question, is dimension of span of F also bounded by maybe some other function of D? Right?
Well, lambda is important. It's bounded by some natural number.
Which can depend on D, right? Because on the degree, if you just take linear forms, we know it's 3. Lambda is 3. If you take quadratic forms also, it can increase. If you take cubic polynomials, it will increase. Okay? But it only depends on the max degree of the polynomials, not on the number of variables. That is the important thing we want. Question?
Transcendence degree.
Yeah, so transcendence degree means you take these polynomials, okay, over C, right? You take these polynomials, they are sitting inside the quotient field of polynomial ring. So it's an extension of C. And then you look at these elements and compute, like, are they algebraic or not over C? Right? So you compute their transcendence degree of, you take C adjoint elements of F and compute transcendence degree of that field extension. All right. Okay. Similarly, we can ask: are these? Is the vector space dimension also bounded? So far the answers are yes in some cases. So D equal to 1 is the classical thing we talked about, right? Sylvester-Galai theorem, many proofs. So yes. So dimension of span is okay. D equal to 2, meaning when we can have quadratic and linear forms. This was proved in 2019 by Amish Pilga. Okay. So this is also yes. This is proved by Spilka in 2019. Okay. And what are we doing is, okay, we want to do it for any degree, but we don't have it yet. We have it for degree 3. Okay. All right. So the theorem that I'm talking about today is this. This is with Rafael Oliveira and myself. Okay. So if F is a 3 radical Sylvester-Galai, meaning polynomials of degree at most 3. Okay, Sylvester-Galai configuration in C x1 up to xn, doesn't matter how many variables are there, then we can also bound the dimension of the span. F, this will be bounded by some constant. Because I have fixed the degree to be 3, I'm not writing lambda of 3. I'm just saying bounded by some constant. So 1. Okay. Question? Okay. Okay, so setting is I have a bunch of polynomials, a finite set of homogeneous forms, homogeneous polynomials inside this polynomial ring of degree at most 3. Okay, and then I'm saying, given any 2, there is a third one in their radical. Then their span must have, there is a universal constant which bounds the dimension of span irrespective of the number of variables of the polynomial.
Can't get any bound on that.
Oh.
10 or 5 or
This one?
can't write an expression.
We have a bound, but it's like exponential, which is not the best bound. Right now, it's just existence. But if it's possible, we can like make it much smaller. Okay, so that's why I'm just writing 4.
We expect some explicit bound, like you have computed up to what?
Yeah, I only have like small examples, like 4, 5, or something. But yeah, because these are hard to construct by hand. But
No conjectural numbers. Like
yeah, not yet. Yeah. Right. Other questions? Okay. How much time do we have? Half an hour. Okay. Good. Right. Other questions? Okay. Right. So yeah. Okay. So why am I? So let me talk about why am I interested in this generalization of Sylvester-Galai, right? And then we talk about how to do it. Okay. So first of all, I find this statement very beautiful mathematically. It's a natural generalization of the linear Sylvester-Galai for polynomials. Essentially, we are saying we have a bunch of hypersurfaces in projective space such that the intersection of any 2 is contained in a third hypersurface. And then somehow we want to say they have large intersection, right? There is some kind of small linear system in which all of them belong. Right?
Could you say something about the concept of the motivation?
That is what I'm going to say right now. Okay. So what is the so other than the mathematical beauty of this statement, what is a practical aspect of this statement is that, so what is the motivation of this conjecture, right? So why did Gupta conjecture this statement? Okay, so that's the motivation. Okay. Motivation is the following. So what computer scientists are interested in is something called polynomial identity testing. Okay. So I give you a polynomial in an arbitrary number of variables, right? Written in some way. You want to check whether this is identically 0 or not. Right? You can have something like x cubed y minus x times x squared y. This is an identically 0 polynomial, right? Suppose I give this to a computer. How does it check that whether it's actually 0 polynomial or not, right? So there are randomized algorithms. You would say, well, if it's the 0 polynomial is 0 everywhere, you choose a random point, evaluate, it should be non-zero if it is a non-zero polynomial. Okay, so there are good, efficient, randomized algorithms, but we always want deterministic algorithms. Okay? There's some philosophy that randomization should not actually help much. Things should be deterministic. I'm not very knowledgeable in that, so let me not say much. But okay, so the question is, I give you some polynomial expression. How do you test? How do you come up with an algorithm whether this polynomial is identically 0 or not, right? For example, maybe I give you an expression like this: P1, P2 times PR plus Q1, Q2 times QS plus R1 ... RT, where all of these are, let's say, irreducible homogeneous polynomials. Pi, Qj, Rk are irreducible homogeneous polynomial. So I took the product of Pi's, product of Qi's, product of Ri's and added them up. I have a polynomial, right? My question is, can you check whether this is a 0 polynomial or not? Okay. So the question is whether it's a 0 polynomial or not. So this is the kind of question they consider in polynomial identity testing, whether this polynomial identity holds. If you want to check whether 2 polynomials are same, you subtract them, you're checking whether it's identically 0 or not. That's why identity test. Any question? Yeah. Everything is in Cx1 up to some number of variables. Okay, arbitrary variables. Okay. So they want to have efficient algorithms for this. Now, how is this connected to Sylvester-Gallai? Right? Okay. So look at this. Suppose it was the zero polynomial. Right? So if zero, then you can say something about the structure of these polynomials. If zero, then look at this. Whenever Pi and Qj vanish at a point, one of the Ri's must vanish. Right? Because if suppose P1 vanishes and Q2 vanishes, then this part is zero. The whole polynomial is zero, so one of the Ri's must vanish. Right? So that's why, right, if it was the zero polynomial, then we have the condition if Pi and Qj vanish, then some Rk vanishes. So which means that for all Pi and Qj, there exists some Rk which is in the radical of Pi and Qj. Right? So Rk inside of radical of Pi and Qj. Right? So yeah, we are in the colored version. Right? So that is the motivation for, right? So it is exactly the thing I talked about. Instead of linear, you just look at this radical colored Sylvester-Gallai. And what Gupta conjectured is that if you can prove a colored version of radical Sylvester-Gallai, then you get polynomial time deterministic algorithms for polynomial identity testing. Yes, that is the motivation, is that the conjecture is essentially okay. So yeah, maybe let me just say it there, right? So Gupta's original conjecture, so he made a series of conjectures, right? So conjecture is, let me just say, colored radical SG holds. Okay, this is the conjecture, and Gupta proved that if this holds, then you get very efficient algorithms for polynomial identity testing. And the theorem of Gupta is that right? So maybe let's call this conjecture 2. Conjecture 1 was the first conjecture. So conjecture 2 implies polynomial time algorithms for polynomial identity testing. Okay. So that is why if we can prove a colored version of radical Sylvester-Gallai, then we will solve this problem, right? So that's the motivation for considering these radical Sylvester-Gallai, other than the fact that it looks nice to me. Okay, question. Okay. Okay, great. Questions so far? Okay. So now we'll talk about how do we prove this thing, right? Okay, great. So this is our theorem. I'm going to rephrase it and write down instructions so that we remember what we actually have at hand. Okay. Right. So this is our result. Right? So we have f inside of C x1 up to xn. Okay. And let's say f is this finite set of forms f1 up to fn. Okay. And what are the conditions we have? Degree of fi is less or equal to 3. Okay. And fi's are irreducible. Number one. Number two, they're not scalar multiples of each other. So fi does not divide fj for I not equal to j. Okay. Okay, so these are two conditions. And number three is our actual thing. For all ij not equal, right? There exists a third polynomial. Fk in the radical of fi fj. Okay, which fk is not equal to fi or fj, a new polynomial. Okay, so under all these conditions, what is our conclusion? Our conclusion is dimension of span of f is bounded by some constant. Right, so let's say O1. Okay, so that's the theorem we are proving. Any question? Okay. Right, so let me talk about what are the ideas in the proof. Question? Okay. Also, before we do this, right, I should give an example of such a thing. Okay, also in this Olivier. Huh? Okay, example. You can make this example, right? So let's say inside of C, X, Y, Z, I'll have 4 polynomials, right? F1 is given by X squared Z plus X, Y squared plus Y cube. Okay. F2 is F1 plus Y cube. Okay, so I'm going to take X squared Z plus XY squared plus 2Y cube. And F3 is just X and F4 is Y. Okay. And then if you take F, which is F1, F2, F3, F4, this is a 3 radical Sylvester line, right? All the polynomials are homogeneous of degree at most 3, and you can check that they satisfy this condition, right? For example, if you take F1 and F2, their difference is Y cube. So Y is in the radical of F1. Okay. X and Y, everything is in XY. So, right? So you can check this is Sylvester line configuration, and they're all linearly independent. So span will be 4. Right? So we're not restricted to 3, unlike the linear case. Yes, this is a true example of non-linear Sylvester line. And you can generate more examples. In arbitrary degree, you can do this yes, with more polynomials.
Okay. Then this condition on M.
No condition on M. That's the thing, right? We don't want independent of N and M. Okay, so that's the most important thing, right? We need to bound, and that's why it's hard. Bound independent of N and M. Okay. Yeah. Right. Okay, good. Question. Okay. All right. So the proof, it involves a lot of like algebraic geometry and commutative algebra. So I'm going to talk about maybe 2 ingredients that we use, which I think are interesting. Okay. So like the algebraic geometry and commutative algebra we use is not too advanced. Okay, it's not something crazy, but yeah, but it's a 2 ingredients. Okay, right. So, right. So first of all, so number 1, right? So this is number 3, 3.1. So you might ask, well, what if the configuration I start with, what if it was actually linear? There is no radical, everything is in the span, right? That can happen. Then we know from the classical thing that we know a bound on linear Sylvester line, right? So it can happen. So if, suppose Fi Fj is radical for all Ij, I mean, this does not happen, but if this happens, right, then let's see what happens. Okay, suppose Fi Fj is radical for all Ij. Then what do we get? Right? This means we are simply saying Fk is in the ideal FIFG. Right? Okay, and let's pretend for a second that all forms of same degree. All forms of same degree. Then, if you have 2 polynomials of degree d, a third polynomial of degree d is in the ideal, it has to be in the span. Right? This is if and only if Fk is in the span of Fi, Fj. Right? So in this special case, it is just a linear Sylvester-Gallai configuration. You have a bunch of vectors, all of polynomials of degree d, you can think of vectors used, right? Just look at the coefficients of the polynomials. And then if all of them were, all pairs were radical, it is just an instance of linear Sylvester-Gallai. So in this case, we would know the answer. Okay, question? Okay, so in this case, we would know the answer. So the main thing we first look at is, when is such an ideal not radical? Okay, because if everything was radical, everything is good, there is nothing to do, right? So question is when, because we're looking at degree at most 3, let me just say when we have 2 polynomials of degree 3. So when is Fi, Fj not radical? When degree of Fi equal to degree of Fj is equal to 3. So I'm asking, I have 2 irreducible homogeneous polynomials of degree 3. When is the ideal not radical? Okay. Can we get some structure about these polynomials under the assumption that the ideal is not radical? Okay. So what do we prove? Right? We can actually get some structure which essentially tells us that these polynomials have to be small prime ideals. Okay. So we can look at the minimal primes of this and we can say what the minimal primes have to be if it's not radical. Okay, so let me write that. So that is one of the ingredients in our proof, is this structure theorem. Right? So, okay, so I'm calling it theorem because previously people proved these things for lower degree and called it theorems, but this is essentially like a lemma. It's not, it's very easy. Okay. So if you have F1, F2, so this is the structure theorem. F1, F2, and degree equal to 3 for both of them, and inside of C, x1 up to xn, okay? Then one of the following holds. One of the following. Okay. Number 1, the ideal can be radical, right? Then we are good. We don't have to do anything. This is a radical ideal. Okay. Number 2, if it is not radical, what are the possibilities, right? Can we find some nice minimal primes? Okay. So number 2, there exists a linear minimal prime. Meaning that there exists 2 linear forms xy which contain f1 and f2. Okay, these are linear forms and linearly independent, right? So this is the prime of codimension 2 and it's a linear minimal. Okay. Number 3, what can happen, right? So there exists a quadratic minimal prime. Okay, so there exists a prime ideal like this, Q comma L, where Q is a quadratic form, L is a linear form, and this contains both of our polynomials. Okay. Number 4, what can happen is that there exist linear forms xy such that xy square is in the span of f1 and 2. Okay. Note that in this case, right, you can right away see that it's not radical. If xy square is in the span, xy is in the radical, but it's not in the ideal. Okay. So this can happen, okay? And number 5, so this is the last thing, right? So let me write it out. There exists a minimal prime P containing, so minimal prime over this ideal f1, f2, such that we know what P looks like. Generators are very simple, such that P is generated by 3 quadratic forms, Q1, Q2, Q3, okay? And let me say what these 3 forms are. QIs are maximal minors of nice matrices, okay, of something like this: y0, y1, y2, y1, y2, y3, and 2 more matrices. Okay, where yi's are linear forms. So that's the structure result, right? So let's look at it for a second and see what it means, right? So I'm taking two polynomials of degree 3. Okay, I have to also add the irreducible and homogeneous forms of degree 3. Then either the ideal is radical, or we know we have very nice minimal primes, which we can control. We know what kind of minimal primes will be there. Either there is a linear minimal prime or a quadratic, or we have something like this in the span, or there is a minimal prime which is given by 3 quadratic forms, which are 2 cross 2 minors of these kind of matrices. Okay, so there are not many choices. Okay, right? So let me just sketch how does this proof work, because it's kind of simple, and then I talk about the other ingredient. Okay, and why this kind of structure theorem should help us. Okay, so let's see that. Okay, right? So I'm asking, my question is, okay, so proof, okay, so proof is, okay, before the proof, maybe I should say that this generalizes previous results. So generalizes some results by Theorem, Sansuk, and Swinnerton-Dyer. Okay, and also Spilka, who proved the degree 2 case. So Spilka also proved something like, instead of degree 3, proved degree 2. These are all for degree 2. And I also did this with Aviv Garg and Oliveira in some other work. And myself. Okay, so in degree 2. If we had degree 2, it's even simpler. I mean, it's not really a theorem. It's just part of the ingredients in all of these papers, right? And so this generalizes those things. And how do we prove this? The technique is simple. Okay, I have 2 cubic hypersurfaces. I'm looking at their complete intersection, right? So it will give me something like this with some number of components, and each of the components will have some multiplicity, right? M1, M2, M3. Okay, so I'm saying that V is, let's say, the scheme defined by F1, F2, right? Inside of Pn or Pn minus 1, right? C, where n variables. Okay, and then if I look at this V, then what is the degree? It's the complete intersection. Degree of V has to be 9, right? And V will have a bunch of components, right? V1, V2, V3, and so on, right? And what does it tell us? That degree of V should be equal to sum over multiplicity times degree of the components, right? Okay. So this is like, yeah. Okay, right? So on this side is 9, right? And we are also assuming it's not radical, right? So not radical implies there exists mi which is greater than 1. If all the components are reduced, it will be a radical ideal. Right? So there is some mi which is greater. Question? Some mi which is greater than 1, right? And then you just do some arithmetic, see what are the possibilities, right? If there exists Vi with degree of Vi equal to 1, suppose there is a component which is a degree 1 component. What can it be? It's this intersection of 2 hyperplanes. It's the linear subvariety. That's the first case. These are the hyperplanes. Okay. If there exists, so this gives us case 1. If there exists Vi with degree of Vi equal to 2, then you have a codimension 2 subvariety of degree 2. Then it has to be given by a quadratic and a linear form. So this gives you condition 2. Okay. Number 3, right? Okay. So if you assume none of these to happen, all components of degree at least 3, right? So then what happens? Then the last 2 cases appear. All component of degree greater than equal to 3. Okay, now this has to sum up to 9. These are, we are assuming greater than equal to 3. There is at least one which is greater than 1. You'll see that if you just do it, you'll see that there are only 2 possibilities. Either you must have 3v1 or 2v1 plus v2, both of them are of degree 3. And in each case, what do we get, right? So this is how that comes. So we consider two cases. So if VI, all VI are degenerate, meaning there are hyperplanes which contain these components. Okay. Suppose in this case, V1 is contained inside V of some linear form L. Then you can show that L cube has to be in the ideal F1, F2. In the second case, suppose V1, V2 both are degenerate. They are contained in hyperplanes L1, L2. Then you can show that L1 square L2 is in the span. If all these VIs are degenerate. Okay, you can prove, it requires a proof, but we can do it. So that's how we get condition 4. And what about condition 5? How do we get this maximal minus and structure? Is okay, let me say here. Is now we can assume that all of them are non-degenerate. There exists one non-degenerate. There exists one non-degenerate PI, which is degree 3, right? And what is the codimension? Codimension is 2. So this means this is a variety of minimal degree. So there is a thing that if you take a variety inside of Pn, which is not contained inside a hyperplane, then there is this inequality that degree is greater than or equal to codimension plus 1. And when we have an equality, they are varieties of minimal degree. And in this case, we have equality. Degree is codimension plus 1. So this implies Vi is a variety of minimal possible degree. And varieties of minimal degree are classified. They are rational normal scrolls. We know their equations. They come from determinants of such matrices. Okay, so this gives us the determinants of matrices. Okay, so this is how we prove this theorem. Question? Okay, question? Okay, how much time? 4 minutes. Okay, not bad. Okay, I'll just talk about the last ingredient, which is kind of the most important thing. So, okay, so this one was kind of basic, it's not trivial. And then the other ingredient is, let's talk about Stillman's conjecture in commutative algebra. Okay, so what is Stillman's conjecture? Let's say K is an algebraically closed field. Okay, then Stillman asked this question: if I take an ideal inside of the polynomial ring, let's call it R. Okay, I'm taking an ideal. It is generated by m forms of degree at most d. So degree less or equal to d. Okay. So inside a polynomial ring in n variables, I'm looking at an ideal generated by m forms of degree at most d. Okay. Then Stillman asked this question and conjectured. So Stillman's conjecture was that the projective dimension of over R of this ideal, or the quotient R mod I, is bounded by some constant independent of n, independent of the number of variables. So what Stillman's conjecture was that you take an ideal generated by m forms of degree at most d, you can bound its projective dimension independent of the number of variables in the polynomial ring and also independent of the field. Okay, that was a conjecture, and this was proved first proved by Ananyan and Hofstede. So theorem, and there have been many subsequent proofs. This was a breakthrough in commutative algebra, and they proved very nice things. Okay, so in 2016, so what did they prove? They proved that there exists a function p of m comma d, a bound depending on the number of generators and the degree, such that projective dimension is bounded by that number. Such that projective dimension of R mod I is bounded by p of m comma d. independent of the number of variables and the field. Okay, so this is what Stillman's conjecture was, and it was proved by Anand and Hofstede. And now you can imagine our situation looks kind of similar, right? If I think of my Sylvester-Gallai configuration and take the ideal generated by that, okay, that can be an ideal generated by m forms of degree at most d, right? And there they are bounding the projective dimension. But how are they bounding the projective dimension is what helps us. Okay, so that's the last thing I'll say and stop, is how do Anand and Hofstede do it? Okay, so I'll just say Anand and Hofstede construct a small subalgebra. Subalgebra, so meaning some subalgebra A, which looks like generated by some polynomial G1 up to Gs, where the number of generators is less or equal to D M P, such that all generators of I are contained inside this subalgebra. So we started with this ideal. Now you can find a small subalgebra of the polynomial ring which contains all the generators. Now by Hilbert's syzygy theorem, this, okay, and they also do more. This is actually isomorphic to a polynomial ring, and projective dimension of ideals in this is bounded by S. This is Hilbert's syzygy theorem. And you can show that this projective dimension is bounded by the projective dimension for A, which is bounded by the number of variables in A. That's how they do it. So the main thing they do is come up with this small subalgebra. And in our case, if we can come up with a small subalgebra, all polynomials are inside this, then you can imagine that their vector space dimension is bounded. You can count how many forms of degree D will be there if you know the number of variables. So it's not immediate from their proof. A lot of algebraic geometry and combinatorics goes into it. It's not immediate, but this is essentially the key idea. So I'll stop here.
Very good.
I think it's a very great for degree 3 to homogeneous. It's for degree 3 or is it for actually?
So which one? Say it again.
Defines F1, F2 to homogeneous if they are classified in
5 cases, yeah. Both of them are of degree 3. Both of them are of degree 3. Yeah, if you take degree 3 and 2, you will have some other cases, which we don't really use. But you can take 2 to 3 to 3 3. At some point, it just becomes too much. You can't do it by hand. So that's kind of the obstruction right now. If you take degree D, degree E, it's hard. Then you're essentially classifying all varieties, all minimal prime, which is like impossible, right? So that's the hard thing. But if you up to degree 3, you can do it by hand. But I just stated why both of them are of degree. Question?
Some slightly irrelevant question.
Yeah, sure.
Because this is about 2 points I'm looking at the line.
Right.
So we looked at the generalization. Is there any kind of thing for 3 points? And
Yes, yes. So these computer science people, they have also proved it for like flats inside affine space. Yeah, that also works. You can bound the dimension. You have this.
What is the status of just for 3? Suppose I got 3, then there's one more. So in Rn you can predict some things contained planar.
Right.
And in Cn maybe like a
CN also you can bound.
space or a planar or how it goes.
I think you bound it by. Okay, I don't remember the number, but there is a number. It's like 9 or 12 or 20 or something like that. It's depending on the. They prove it.
Yeah. I couldn't get as to how you would construct such configurations in general. I mean, just want to know what is the underlying principle behind getting such configurations. I mean, I didn't understand.
So yeah, that's a good question. I don't have a way to construct them by hand. I don't have a good way. I can only make up examples which don't have which don't come from a general philosophy. So I don't have a good answer to that. How to construct these configurations in general. I can come up with some examples here and there. And the other thing, my guess is where they would come from. If you have a polynomial identity, then you can of course generate the colored versions. That we will be able to generate if you take some polynomial expression which is equal to 0, and then you take the polynomials from them, you can generate colored radical Sylvester-Gallai. But without the colored version, I don't know how to generate them in general.
Is there something like a group law underlying somewhere? I mean, some vague question I'm asking. Sorry.
Yeah, that's possible. I have to think about it. I don't know right now how to generate them. Yeah. Like the only thing is that the linear case, we had that inflection points, right? So maybe there is something geometric in like for polynomials, which I don't know right now. Yeah.
Are there any more questions? It's not let's hang this. At 12.
Should I share the screen?
Sir, 2 minutes, sir. Please wait 2 minutes. Deep break.
I still it. Hello, can you hear me? Yes, Nandit. So we will actually resume at 12. So you can share with your.
So when will the talk will start?
Hello, Snehajit, are you there? Hello. হ্যালো, তুমি শুনতে পাচ্ছ না? Not able to. They are saying they are able to hear. Hello. কিন্তু এখানে লোকেরা শুনতে পাচ্ছে বলছি, যারা অনলাইন। কিন্তু তুমি আমাকে ভয়েস শুনতে পাচ্ছ না? হ্যালো। He's not able to hear you. So they're suggesting you log out and log in. Then
Here I can give you
hello. Hello, Snehajit.
Now I can hear. Sorry for the disturbance.
Okay. You can hear us clearly, right? Hello.
Yeah. I will just share the screen. Is this visible to everyone?
Yes, it is visible.
Okay. Okay, I think we can start.
Okay, so welcome back everyone. So our next speaker is Dr. Snehajit Mishra from CMI Chennai. He will speak on Seshadri constants for parabolic ample bundles. Over to you, Snehajit.
Okay, thank you very much to the organizers for inviting me to give this talk. So as the title suggests, I will speak on Seshadri constant for parabolic bundles. So this is based on a joint work with Indranil Biswas, Krishna Hanumanto and Navanita Ray. Okay, so let me start with defining what is an ample line bundle. So throughout this talk, we will consider only projective varieties which are defined over complex numbers. And suppose L is a line bundle on such projective variety X, and we choose a basis for the space of global sections of the line bundle. So using this basis, we can define a rational map to the projective space just by evaluating this complex basis. But this is not completely defined on whole of X, because all the sections might vanish at some point of X. And so this map is precisely not defined on the base locus, which is the intersection of the zero sets of all these sections. So we'll call this line bundle L as base point free or globally generated if the base locus is empty. That means we can define a full map phi L from the whole of X to the projective space just by evaluating the sections. Moreover, in addition, if phi L defines a closed embedding inside the projective space, we'll call the line bundle as very ample. So clearly the very ampleness of a line bundle is very important as far as the closed embedding in projective spaces are concerned. And a line bundle is called ample. This is just terminology. A line bundle is called ample if some positive integral multiple of it is very ample. Okay. So next we restrict our attention to a special class of line bundles, which are called Neff line bundles. So a line bundle on a projective variety is called Neff if its intersection with every irreducible curve is non-negative. And Harshan has extended this notion of Neffness and ampleness for line bundles to the case of vector bundles. So he defined a vector bundle on a projective variety X is to be Neff or ample if the relative O1 on the projective bundle P of E is ample or Neff. All right. So we have extended the definition of Neffness and ampleness in the case of vector bundles. Okay. Sometimes we have to deal with real coefficients, so which I am going to define now. So R divisor is an element in div of X tensor R, where div of X denotes the divisor group of X. And such an R divisor will look like some AIDI, where AI are real numbers which are zero except finitely many, and DIs are Cartier divisors on X. So such a divisor D is called numerically trivial if its intersection with every curve C is 0. Now, if I consider the quotient of this div of X tensor R under this equivalence relation, the quotient is called the real Lorentz-Every group of X, which we will denote as n of X of R. In fact, this is a real dimension, finite dimensional real vector space, and an R divisor on X is called Neff if its intersection with every irreducible curve is non-negative. So we have extended the notion of Neff line bundles to real R divisors. Now, this intersection product being independent of numerical equivalence class, one can talk about Neff classes in this real Lorentz-Every group of X. So we'll often talk about numerical equivalence classes in this real Lorentz-Every group. Okay, so there are some criteria for ampleness. One is due to Grothendieck, and there are some cohomological criteria due to Serre for ampleness. But for this talk, we are mainly interested about numerical criteria for ampleness. One such is given by Nakai, Mosesian, and Kleiman. So it basically says that a line bundle on a projective variety X is ample if this kind of intersection product L to the power dimension of V intersected with V is positive for every positive dimensional irreducible closed subvariety. And this positive dimensional irreducible closed subvariety should also include the irreducible components of X. So in particular, if you replace this V by any smooth curve or any curve in fact in X, it shows that L dot C is positive. So this criteria is basically saying that any ample line bundle is actually Neff. And the other criteria is due to Seshadri, which is that a line bundle is ample if there exists a positive number epsilon such that this fraction L dot C divided by the multiplicity of the curve C at the point X is bigger than equals to this epsilon. So it's basically saying that the degree of the line bundle restricted to every curve can be bounded from below up to multiplicity, and this should hold for every points of x and every irreducible curve passing through the points of x. So this is quite strange that ampleness is a global property, though the ampleness is captured locally. So this is quite interesting. All right. So so these are the two criteria that will be important for our talk, and based on these two criteria, we will define the Sesardi constant. So let me come to the definition of Sesardi constant for line bundles. So we fix an F line bundle on a complex projective variety. So the Sesardi constant was introduced by de Mailly in order to tackle Fujita conjecture, and it was inspired by the Sesardi's criteria for ampleness. So for a point x in x, the Sesardi constant of the NAP line bundle L at x, which will denote by var epsilon x L at x, which is defined as the infimum of this kind of fractions L dot C divided by the multiplicity of the curve C passing through x, and this infimum is taken over all irreducible and reduced curves passing through x with multiplicity this. So although de Mailly defined it for Fujita conjecture, it turns out that his approach is not quite suitable to prove Fujita conjecture, because the Sesardi constant can take arbitrarily small values, which is the main difficulty while proving Fujita conjecture using Sesardi constant. Although this constant plays a lot of useful role to study local positivity of the line bundles as well as interpolation problems and a lot of things. So it has wide applications, and it is not quite difficult to show that this definition is equivalent to the definition that I am going to state now. So if you blow up the x at the point x, and if you take the supremum of real numbers, non-negative real numbers, such that pi star of L minus lambda of E is NAF, but E is the exceptional divisor corresponding to this blow-up map, then this supremum is equal to the Sesardi constant, which is defined as the infimum of these kind of fractions. And this definition will be useful when we will try to extend this definition for Sesardi constant of line bundles to the vector bundle case. So next we go to the Sesardi constant for vector bundles. So if I start with a naive vector bundle on a projective variety and fix a point x in x, I just blow up the point x in x and consider the projectivization of E, and I further blow up P of E along the fibers over x. So this is this is the commutative diagram, and this is the blow up of P of E along the fibers over x. So I denote Ex tilde to be the numerical equivalence class of the tautological bundle on this projective bundle over the blow up, and this is just the pullback of the exceptional divisors here. And Hakon introduced this notion for Sesardi constant for vector bundles, which is defined as the supremum of positive real numbers, such that this E tilde x minus lambda of E of x tilde is NAF. And one point I want to emphasize that it may look like that this is the Sesardi constant of O relative O1 of P of E, but remember that the point x lies on x and O1 lies on P of E. So this is not exactly the Sesardi constant of the relative O1 of P of E. So instead of blowing up some point, we are blowing up fibers over the point on P of E. So this is not exactly equal to the Sesardi constant of the relative O1 on P of E. Okay. So now I'll come to the main objects for this talk, which are parabolic vector bundles. And we want to introduce the notion of Seshadi constant for parabolic vector bundles, which will generalize this concept of Seshadi constant for line bundles and vector bundles. So let X be a connected smooth complex projective variety of dimension D, and we will fix an effective divisors on X. And let E be a torsion-free coherent OX module, a quasi-parabolic structure on E with respect to the chosen effective divisor is a filtration of OX coherent subsets. So this is a filtration of OX coherent subsets starting with E of minus D. And the length of the filtration is the integer L here. A parabolic structure on E with respect to the chosen effective divisor D is a quasi-parabolic structure as above, together with a system of weights which are nothing but a tuple of real numbers, where alpha 1, alpha 2, alpha L are real numbers lying between 0 and 1, and these numbers are called parabolic weights. And each alpha I we say is attached to Fi of E, where Fi are the intermediate OX coherent subsets of E. A parabolic vector bundle with parabolic divisor D is a vector bundle E with a parabolic structure with respect to a effective divisor D. So for any parabolic vector bundle E star, which we defined just now, and for any real number, we can define the filtration Et, which is defined in this fashion. It is Fi of E, where Fi of E is coming from the filtration of the parabolic bundle E star, twisted by the integral part of T of D. Okay, so this filtration Et determines the parabolic structure on E. So sometimes we will just denote E star instead of E comma F star comma alpha star, just to denote the parabolic bundle. Now, if you consider the effective divisor D, and if you break it into its reduced irreducible divisors Di with coefficients Ni, and consider the inclusion map along these subschemes Nj, Dj. For each such Fj, you can choose a filtration and fix some real numbers depending on the length of the filtration, which lies between 0 and 1. And for every component Dj of D and every K which lies in between the length of the filtration of this, we define the coherent subsheaf Fj bar using this exact sequence. And we can define Ljt to be the smallest number in the set of integers like this, where alpha j are the parabolic weights. And we just set Et to be this, which are a subsheaf of E of the fractional part of T of D. Now this the filtration defined in this fashion, Et in 4, it indeed defines a parabolic structure on E, and it is a straightforward checking that all such parabolic structure on E with D as the parabolic divisor arises in this way. So from now on, we will be dealing with parabolic bundles with rational coefficients. So we will impose these 4 conditions on our parabolic bundles. Namely, we will start with parabolic divisors, which are simple normal crossing divisors. That means the coefficients Ni is 1 and Di's are smooth divisors, and they intersect transversely to each other. And for each component Di, the filtration that we chosen if you can go back to this slide, this filtration. The filtration chosen in such a way that all these Fij are subbundles of Fi star of V. Remember that Fj was the inclusion of Di inside D. And we choose these weights are to be rational, so that you can write this alpha ij to be some Mij quotiented by n, where n is some fixed integer and Mij belongs to numbers between 0 and n minus 1. So, and also for every point x of D, one has a neighborhood ux and a decomposition of E restricted to ux into a direct sum of line bundles, such that the filtration of E restricted to ux intersection Di are constructed using this decomposition. So we put these 4 conditions to use some kind of correspondence, which I will explain now. So parabolic vector bundles with rational coefficients will have a natural correspondence with orbifold bundles, which I'm going to explain now. So let gamma be a finite group acting on a projective variety Y. So our orbifold bundle on Y with gamma as the orbifold group is a vector bundle on Y together with a lift of the action on Y, which means that for any G in this finite group gamma gives a vector bundle isomorphism between V and psi of G inverse pullback of V. So this is the definition of an orbifold bundle, and there is a construction from going from a parabolic bundle to the associated orbifold bundle, and from orbifold bundle to the parabolic bundle. And this is a theorem due to Viswas that if E star is a parabolic bundle on X, then using the Kawamata cover with a finite Galois group, one can construct an orbifold bundle E prime on Y, such that the parabolic bundle E star is recovered from it by taking the gamma invariance of the direct image of the some kind of twists of E prime using the irreducible components of the divisor D, effective divisor D. So this is kind of a one-to-one correspondence between the orbifold bundles and the parabolic bundles on X. So for every parabolic bundles on X, you can construct an orbifold bundle on Y, and similarly for an orbifold bundle on Y, if you consider the lambda invariance of the direct image of the twist of E prime, you get back the parabolic bundle. So we're going to use these correspondence later on. Again, the parabolic ampleness is introduced by Viswas. So a parabolic bundle E star is parabolic ample or respectively parabolic nave if the corresponding orbifold bundle E prime is ample. E prime is a vector bundle on Y. So E prime is ample or respectively nave as a vector bundle in the sense of Hartshorne that we have already mentioned. I must mention that parabolic ampleness can be defined in a more general setup, but since we are restricting ourselves to the parabolic vector bundles with rational coefficients, we will take this as the definition. So parabolic bundles can be defined without the assumption that the weights are rational, or the 4 assumptions that I took. Okay. So while defining the Seshadri constant for parabolic bundles, one of the difficulty is to define the projectivization of the parabolic bundle. And this is done by again identifying parabolic bundles with ramified bundles. So on a smooth complex projective variety with a normal crossing divisor D, a ramified principal GLNC bundle with ramification over D is a smooth complex quasi-projective variety EGLNC. So the total space is called the EGLNC, which has a algebraic right action of the general linear group, which satisfies these 5 conditions. So the action should be compatible with the projection, the first condition. For every point x in X, if you consider the reduced fibers over X, the action of the general linear group is transitive. And this is sort of principal bundles outside D. So the restriction of phi to phi inverse x minus d is a principal GLNC bundle over x minus d. And for each irreducible component, di of the SNC divisor d, the reduced inverse image is a smooth divisor, and you can write it as phi inverse of di, where this phi inverse of di is a normal crossing divisor on the total space EGLNC. And for every point x in the divisor d, and for any point on the fiber over x, the isotropy subgroup for the action of the GLNC on the total space EGLNC is a finite group. And if x is a smooth point of D, then the natural action of the isotropic group on the quotient line bundle, the tangent bundle of the total at the point z, quotiented by this T of z phi inverse of D reduced, is faithful. So these are the 5 conditions one has to satisfy to call it as a ramified bundle. This is called ramified because it's almost like a principal bundle outside the ramification divisor. And there is a correspondence between parabolic bundles and ramified bundles, which generalize the known bijective correspondence between the complex vector bundles on X and the principal GLNC bundles on X. So basically, this correspondence sends a principal GLNC bundle to the vector bundle given by the diagonal action, right action on this product F cross Cn associated to F. So this is a fiber bundle. In fact, it's a vector bundle with fiber GLNC. And it's a fiber bundle with fiber Cn, and this correspondence extends to a bijective correspondence between the ramified principal GLNC bundles with ramification over D and the parabolic vector bundles of rank n with D as the parabolic divisor. So there is a correspondence between principal bundles and the complex vector bundles, and this correspondence generalizes to the ramified principal bundles with parabolic vector bundles. We are going to use this correspondence to define the projectivization of a parabolic bundle. And this has been done in a paper due to Biswas and Fatima Laitimi. So if you start with a parabolic vector bundle and you consider the associated ramified bundle, EGLNC, consider the standard action of the general linear group on Cn, then it induces an action on the projective space Pn minus 1. And the projectivization of E star is defined to be the associated fiber bundle, which is again the diagonal action on EGLNC cross Pn minus 1 over X. Okay, so we have constructed P of E star, but we still haven't defined what should be the correct notion of relative O1 on this projectivization. Before going into that, we want to define something. So for any point x in the divisor D, if you take z on a fiber on the fiber over x, and if nx be the order of the finite group z, g of g. So remember that in the definition of ramified bundles, we want this isotropic group to be of finite order, and the number of distinct integers nx as x varies over D is finite because of the transitivity of the action. And we consider the LCM of these finitely many integers where x varies over the divisor D. We call this to be n of E star. Now, if you consider the action of GLNC on the total space of the Serre bundle with a twist by n of E star using the standard action on Cn, And then again, you can construct this fiber bundle. As the natural projection map intertwines the action of the general linear group on this line bundle and Pn. So it produces a projection to P of E star. And we will call this line bundle to be the tautological line bundle on P of E star. So though I didn't prove it why this should be an algebraic vector bundle, but that I leave aside because that will take some more time. So just believe that this is a algebraic vector bundle on P of E star. And we are now all set to define Seshavi constant for parabolic vector bundles. All right. So taking a cue from the case of vector bundles, we define parabolic Seshavi constant for a parabolic naive vector bundles. So we consider this P of E star over X, this projection map, and we blow up at a point X and consider the fiber product, which is nothing but the blow up of P of E star along the fibers over X. And the parabolic Seshavi constant of each star at a point X is defined as supremum of positive real numbers, such that the psi x tilde star of xi minus lambda rho tilde star of E of X is naive, where E of X is the exceptional divisor of this blow up map, and xi is the numerical class of the tautological bundle that we have constructed. Not we have constructed. Construction was due to Biswas and Laitini. So this xi is the numerical class of this tautological line bundle. Okay, so this is quite straightforward if you consider the case of vector bundles and how the Seshavi constant for vector bundles are defined. But we want a definition which is like to the case of line bundles, which is like infimum over some curves and the taking fraction of the intersection product divided by the multiplicity. So next we'll see a characterization of such a for such a parabolic naive vector bundles. So if we start with a parabolic naive vector bundles on a smooth projective variety X, and if you fix a point X in X, and I consider the set of all integral curves in this projectivization P of E star, which intersect the curve over X, rho inverse X, while not being contained in it. So this curve should give a non-constant map to X. This is not contained in a fiber. I am collecting all such integral curves. So then one can show that the Seshavi constant that we have already defined is equal to the infimum of xi dot c, where xi is the, if you can go back to the previous slide, xi was the numerical class of O1 on P of E star. This xi dot c divided by the multiplicity of rho star c. So rho star c is a curve here, and it passes through the point X because it intersects the fiber rho of X. And if you consider the multiplicity of rho star c at X, and I am taking infimum over all curves which are intersecting the fiber rho over X and not containing it. So this multiplicity is strictly positive. So now we have shown that both the definitions are quite compatible, like in the sense that one is defined in terms of supremum of some certain class is naive, and one is as the infimum of some fractions. Now we want to see a relation between parabolic naive vector bundles and the corresponding associated orbifold bundles, and what is their relation of the corresponding Seshavi constant. So remember that if we fix a parabolic naive vector bundle, then the associated orbifold bundle is naive in the usual sense as a vector bundle. So the Seshavi constant makes sense We'll see what is the relation between them. So let E prime be the corresponding orbifold bundle over Y of a parabolic name vector bundle on X with Galois group gamma. And we have this following fiber product diagram. So for any X in X, I can consider gamma inverse X, which is a finite set equal to the cardinality of gamma. And I can blow up Y along these finitely many sets, and I can consider the fiber product. So, and also we have P of E star over X, which is equal to quotient of P of E prime mod gamma. And E of gamma inverse X be the exceptional divisor on this, on Y. Then one can show that the Seshadri constant is equal to n of E star times supremum of lambda positive real numbers, such that this under this phi x tilde star of xi prime, where xi prime is the tautological bundle of P of E prime minus lambda times tau tilde of pullback of the exceptional divisor is nef. So you can, I mean, we have not used this this terminology, but you can think of it. This term is kind of multi-point Seshadri constant of the vector bundle E prime, but there is no such notions in the in language. But this supremum of this part can be think of it as multi-point Seshadri constant of E prime along gamma inverse of X. Note that gamma inverse of X, though it have cardinality mod gamma, the number of points may be less than mod gamma, precisely over the points over the divisor D. And similarly, we have a similar expression in terms of the infimum of xi prime dot C quotiented by this kind of multiplicity, where the curve, considering the curve which intersect gamma inverse of X, and this multiplicity is strictly positive. I mean, it intersect gamma inverse of X, but not entirely containing gamma inverse of X. It only intersect gamma inverse of X. So this is the relation between Seshadri constant of E prime and Seshadri constant of E star. Okay, these two characterizations are important to prove our theorem, and we have shown that E star, if E star is a parabolic naive vector bundle, then E star is parabolic ample if and only if infimum of the Seshadri constant at every point of X is strictly positive. And this result generalizes the known results for vector bundles, line bundles on irreducible smooth projectivity. And so the proof of this one uses the alternative characterization that we have used. And using the previous two characterization, we also give this strange looking upper bound of the Seshadri constant. So one point I wanted to mention that this n of E star is defined in terms of the ramified bundle associated to E star. So this also has a role to play while computing the Seshadri constant, parabolic Seshadri constant of E star. Okay, this is just a strange looking upper bound of the parabolic Seshadri constant. Okay. So, I mean, the first obvious case where you can compute the parabolic Seshadri constant is for parabolic naive vector bundles over smooth curves. So, for that we define the parabolic mu mean, which is the parabolic slope. Parabolic slope is the parabolic degree quotiented by the rank of the underlying vector bundle. And this parabolic slope of the minimal parabolic semi-stable subquotients of E star is denoted by the parabolic mu mean of E star. Now, it's not quite difficult by considering just the degree of the associated orbifold bundle and the parabolic vector bundle of E star, one can show that if E prime is the orbifold bundle on Y corresponding to this parabolic vector bundle, then the mu mean of the orbifold bundle is equal to the continuity of the Galois group times parabolic mu mean of E star. And the characterization that we have already proved, or the alternative characterization, we will able to prove that if E star is a parabolic ample vector bundle over a smooth irreducible projective curve with parabolic divisor D, then the parabolic Sheshadi constant is equal to n of E star times parabolic mu mean of E star when x does not belongs to D, and this is greater than equals to n of E star times parabolic mu mean of E star when x belongs to D. So in particular, in both the cases, this is bigger than equals to n of E star divided by the rank of E. So and if you consider E star as a vector bundle only with no parabolic structure, then the D is then empty in that case, and then n of E star will come up as 1. So this result generalizes the known results due to Hakon for Sheshadi constant of vector bundles on smooth curves. All right. Okay. We again proved another result which is useful for computation of Sheshadi constant by reducing the case to the curve. So if E star is a parabolic Neff vector bundle on a smooth irreducible complex projective variety, and E prime is the corresponding orbifold bundle over Y, then the parabolic Sheshadi constant is n of E star times infimum of mu mean of nu star of E prime divided by this multiplicity, where this infimum is taken over all curves in Y which intersect gamma inverse of x. Remember, gamma was the cover Y to x, which intersect gamma inverse of x, and this nu is the normalization map. So this irreducible curve can be non-smooth, so you have to take the normalization. So eventually you are computing the parabolic Sheshadi constant by going to normalization of the irreducible curves of the orbifold bundle on Y. So you have to just consider the mu mean of nu star of E prime restricted to every curve. So this result is useful to prove some of the things that are going to follow. So using this criteria, we proved some results about the Sheshadi constant of symmetric power and tensor product of two parabolic bundles. So let E star and F star are two parabolic Neff vector bundles on smooth irreducible complex projective variety having a common parabolic divisor D. Then if you consider the mth symmetric power, so this is I have not defined the symmetric power of a parabolic vector bundle, but one can use the correspondence with orbifold bundle. So if you consider the orbifold bundle of E star, and if you take the mth symmetric power of the orbifold bundle E prime, and if you get back to the corresponding parabolic bundle, I call it Sm of E star. So the parabolic Sheshadi constant of the mth symmetric power of E star is equal to m times the parabolic bundle, Sheshadi constant of the parabolic bundle of E star. And similarly, we have a formula for Sheshadi constant of the tensor product. Both this computation uses this criteria, because you know how the symmetric power of E star corresponds to the symmetric power of E prime. So this is just m times mu mean of the nu star of E prime. So m is coming out. That's why this homogeneity property is satisfied here. And similarly, in the case of tensor product, you can use this criteria and the properties of mu mean to split between these two things. I think that's all I have to say. Thank you.
Are there any questions? Anything known about non-rational weights? When weights
Yeah,
are
for
not rational?
Yeah, so if it is not rational, I don't know how to define the projectivization. We cannot use this orbifold thing. So I don't, usually if it is not non-rational, then you have to go to algebraic stack, and there things can be complicated. So I don't know till now. I mean, usually this correspondence of Biswas holds in case when there are rational weights. So, and also this ramified thing. If it is not rational, then all this correspondence doesn't hold. So there it's difficult.
We show in the
Yes.
last slide.
Yeah.
Can you say something about the extension? Yeah, last.
Yeah.
Instead of each star S star, if you take more than two parabolic NEF vector bundles, then
Yeah, you can extend this to finitely many vector bundles. That is not a problem. The only thing that it has to be defined for a common parabolic divisor. That's all. So you can take finitely many, and you can take common parabolic divisor. So that is not a problem.
is the parabolic Krishna constant definition is different from what Krishna's definition. Krishna's talking here also defined.
No, so parabolic vector bundles are like vector bundles with a parabolic structure, right? So that's how it is defined. So if you remove the parabolic structure, then the definition is consistent, because you can take this map to be identity, and then see this definition is the same.
Okay, thank you.
Okay, there are no more questions. Let us thank the speakers again.
Okay, thank you.
We'll resume at 2:30.